Okay, let's go ahead and finish some of these notes again. So we ended up talking about weight. And the word weight and mass have two different meanings. They are absolutely not the same thing. Okay? Mass is how much matter that is in that object. Weight is the amount of force due to the gravitational pull on that mass. And I know it says Earth, but it can be anywheres. Okay? So what we're trying to say here is this can change. Because gravity can change. Right? If you were to go to the moon and there's less gravity, then your weight would be less. This will always be the same, no matter what. I don't care if you go to the moon, you're here on Earth, you go to Pluto, you're going to have the same. The mass amount will be the same. It's not going to change. So let's go ahead and let's do our example that we go through here every year. Now, it's a little bit funner when we're actually in class and we can pick on somebody, but they want to know, what is your mass here on Earth? Okay, well, we can find that out. So again, if you're having to do a force equation, which is mass multiplied by acceleration, and you don't have the mass in kilograms, and they give it to you in pounds, you can figure it out. And this is how you're going to figure it out, okay? So your mass on Earth. For us to figure out what your mass is on Earth, when you stand on the scale, your scale tells you how many pounds you are. So let's go ahead and let's just pretend we've got a person here and they're going to stand on a scale. So here they are on the scale. There it is. And they look at their scale and it tells them how many pounds they are. Well, let's go ahead and toss out a make-believe number, and they weigh 170 pounds. Okay? I don't know who this person is, but they weigh 170 pounds. I'm going to need to grab my calculator over here so we can get this math done. Now, for me to figure out how much this person actually has in mass, I need to divide that number by 2.2. So let's get 170 divided by 2.2. It equals the answer of 77.27 kilograms. So what is that person's mass? 77.27 kilograms. Now, if I needed to do a force equation with this person, I would know the acceleration plus their mass in kilograms, and I can do that. Again, you will be given the weight here in pounds, whether it's a quiz question, maybe a homework question, or a test. Please don't get confused, or don't forget that you need to convert that pounds into kilograms, okay? And this is how you do it, by dividing by 2.2. Now, your weight on Earth. Now, let's continue to talk about this. We're going to get this number in kilograms. We're going to bring it over here, which is 77.27 kilograms, and we're going to multiply it because we want to know the weight on Earth. If we want to know the weight on the moon, well, then we would use the moon's gravity. And why are we using 9.81? Remember, the definition for weight is the amount of force due to the gravitational pull on the mass of that object. So we're going to calculate the weight of a person. Well, first we found their mass in kilograms. Now we're going to use that mass number and we're going to find their weight. Their weight is going to be the kilogram number multiplied by the gravity, and we're here on Earth. Well, they even said the word Earth. So now let's go ahead and get that 77.27, and we're going to multiply it by 9.81, And again, I'm not using the negative value because that's only a direction. How much is the person's weight here on Earth? Because when they stood on the scale, it actually said 170 pounds. But their weight here in physics class is 758.05 newtons. That's a lot. That's a lot. Their weight is a lot. So I know when I'm going to stand on the scale, I'm going to make sure that my scale is in pounds, not in newtons. No way. Now, okay, what about your weight? And we're saying this person's weight on the moon. Well, we would get there 77.27 kilograms. So I'm going to take that number over here again. 77.27. And remember, the moon is 6 times smaller or less than Earth. So if I got 9.81, let me go ahead and do this first. 9.81 divided by 6. This number actually comes out to I'm going to do that. I'm going to say it's 1.635. Or you can get this number, multiply it by 9.81, and then divide by 6. Either way, again, right? There's more than one way to do that math. So me personally, I like to go ahead and just knock this out of the way and get a number value. And I'm going to get that number, and I'm going to multiply it by the 77.27 equals, what is their weight on the moon? 126.34. That should be a newton. Who knows what happened here? Newtons on the moon. Okay. How about your mass on the moon? Well, what is your mass? Or again, we're saying the word you, but we mean this person. Go back to the scale. What does their scale read? I'm going to come right here and I'm going to draw an arrow to that scale. And it's kind of, can't read it right here, but it's 170 pounds, right? That's the number we used. So we're going to get that 170 pounds, which is the English system, divided by 2.2. Even on the moon, to find the mass of an object, you get the pounds here on Earth, divided by 2.2. It's still going to be 77.27. Why is that? Because mass never changes. Weight does. So I'm going to do a little arrow here and an arrow right here. And just as a reminder, I wrote it on the previous page, mass never changes. Does not matter if you're on the moon, if you're on Pluto, or if you're on Earth. The mass amount will always stay the same. It says over here, notice that your weight changes because of the force on the moon is less than the force of the gravity on Earth, but your mass will always stay the same. This is because your body contains the same amount of substance, of atoms, of particles, and the same amount of quote unquote stuff, no matter where you go. Now, when would your mass change? Well, what if this person was traveling or doing something and there was an unfortunate accident and they lost both legs? Psh. Sad, yes. But now their mass did change because they lost a big chunk of the amount of stuff on them. If both legs were gone, look at that. Psh, I cut it off right there. Now their mass is going to change. Till something like that happens, your mass is going to remain the same. Now, if you go through some crazy dramatic weight loss and you lost 172 pounds, well, wow, yeah, your mass changed, okay? Until then the mass will remain the same, okay? Weight will change due to the amount of gravity. And if you, I'm not sure if you know this or not, but actually the gravity here on Earth, yes, is negative 9.81. But the gravity on Earth at different locations is different. So the gravitational pull on the north and south pole here on planet Earth is actually a different, slightly, not a lot, different than if you lived on the equator. And if you lived here in Galveston County, right, we are considered to be at sea level. But if you were to live in Colorado or somewhere like really high altitude on a mountain, your gravity pull would be less than here on sea level. And so your weight on the scale, when you stand on the scale, would be a little different because the gravitational pull would be a little different. Okay, I'm going to go through just a little bit of the next part, and then I'm going to stop there because we're going to get into the next kind of math, which is including the SOHCAHTOA like we did previously. I'm going to go ahead then and post the videos that I have now. Tomorrow, I'll go ahead and video the next part. Alrighty, we don't need the rest when it comes to homework number 1 just yet, but I will post that really soon. We're going to talk about this other concept here. It's a new concept. I know that you do not talk about this in middle school or biology or chemistry class. This is a physics concept. But what we've been using, those vector arrows and the SOHCAHTOA, is helping guide us into this, okay? What we call free body diagrams. In physics, we use what we call free body diagrams, which is a diagram or a picture of a single object and all of the forces acting on that object. Again, so far we talked about forces like up and down, and you're going to subtract them. Or both forces are pointing to the left. You're going to add them. Or we talked about a force to the left and up, and then you use SOHCAHTOA or Pythagorean. Okay, now we're going to talk about up, down, right, and left all at the same time. That's what we're going to now. Okay, we're taking it up another notch. It says here, for an example, let's go ahead and draw a free body diagram of the forces that would be acting on this car if it's being towed away by a tow truck. So what are we doing? We're only concerning, or our concern is only regarding the car. I do not care about the tow truck. You're only going to draw that single object. Now, here it is, my car. And my car, it's kind of has, look, it's lifted up because of the tow truck. All right. So we're going to draw that car at an angle because the road is actually, do not draw this when you're doing your free body diagrams. But the road would look like this. Okay. So you can see that this car is not on the road, like all 4 tires are not. We won't even draw the actual road either. That is not even included, but I'm drawing it for you so you can see it at this moment. Now, we're going to talk about 5 different forces. There are a few other forces, but these are the main 5 forces that are used in what we call free body diagram pictures. Okay, our first force is what we call a normal force. Our second force is the applied force. The next force is what we call frictional force. The next force is weight force. Okay. And then the next one is on the next page, which is going to be our tension force. Now I'm going to go back. Now, those forces actually have abbreviations. So to abbreviate those forces, this one is a capital F, little n, sub n, a capital F, sub A capital F, sub F, a capital F, sub W, or a capital F, sub G. Why? Because isn't weight due to the amount of gravitational pull on that object? That's the reason why it could be, we call it weight force or gravitational force. It's the same thing. Okay. And then the next one, right, is the tension force, F sub T. And this is actually a capital little t. It's a little t, but it's a capital. Let's keep going. It says over here, normal force. The normal force is the supported force exerted upon the object that is in contact with another stable object. For an example, if a book is resting upon the surface, then the surface would be maybe the desk, is exerting an upward force on that book. 95% of the time, the normal force is going to be an upward force, an upward arrow. And I'm just saying 95% of the time. Let's just say right now you're sitting on a chair at your desk. That chair is the normal force pushing and holding your butt up. Okay? So my paper is on my desk. The normal force is the desk pushing up on my paper, holding it up. Okay? The next one, applied force. Applied force is a force that is applied to an object by a person or another object, like an engine. If a person is pushing a desk across the room, then there is an applied force acting upon the object, which would be the desk. The applied force is the force exerted on the desk, which is from that person, that is by the person. So applied force, you kick a ball, that's an applied force. You got mad because of your video game and you're raging, you toss your Xbox controller down, that was the applied force. What if I have a pen in my hand and I let it go? The applied force is gravity pulling down at that time. Okay, but we are not going to use applied force. We would use gravitational force. Okay, I just want to make sure I clarify that when it comes to that. A car driving, the engine is the applied force to cause the car to move. Frictional force is just like how it says, right? Now, it is also considered to be air resistance. Okay, is a frictional force, which is the force that's exerted by a surface as an object moves across it or makes an effort to move across it. Okay, though it is not always that case, the frictional force often is 99% of the times is going to be an opposite to the motion or opposite to the applied force. Okay, 99% of the time, that will be the case. Weight force, which is also the force of gravity, right? We talked about that definition, is the force with which the earth, moon, or any other massive object attracts another object towards itself. By definition, this is the weight of the object, not the mass. Not the mass. Okay. And then the last one over here, which is tension force. Tension force, it says here, let me turn my notes so I can have my notes with me. Tension force in an object results if pulling force is acting upon it. Acts on its ends, such as in a rope used to pull a boulder, I don't know. If no forces are acting on the rope, say except that end of that rope itself, then it is considered to be in equilibrium. For an example, an object is just hanging at rest on a rope. Okay? It's just hanging there on a rope. It's at rest. Then the tension is going to be the same throughout the rope. Okay? And that is something, I don't know if it's quizzed or test question, but that will be on there. A couple of examples would be, yes, they said rope, a string, a chain like a necklace or something. Okay? I'm sure there's other examples too, but those are the most common examples. Okay? Now, before we get into this part, which I will start recording tomorrow, because yes, we're going to start talking about all the forces acting on one object and finding the resultant vector regarding the direction and the magnitude of that object. Okay? Then we get into our last equation. But there was a little section over here that I left off. So let's go ahead and talk about this section. Let's go ahead and draw the free body diagram vectors that go along with it. And then we're done for today. I'll video again tomorrow. But before we continue, objects do not always have all 5 forces working on them. We talked about 1, 2, 3, 4, and then tension is 5. Okay? Some objects will only have 2. Some of them will have 3. Some objects will have 4 vectors acting on it. I might have a free body diagram that has all 5 of those forces acting on it, but it doesn't have to. All right? Let's go ahead and let's take a picture, or let's look at this picture, of the car. The first thing is, when we do free body diagrams, we always start from the center of that object. There it is. Okay? Now, I have to imagine, here's the car. It's like tilted up at an angle. Okay? The first thing that I do know is that whether this car is tilted at this angle or whether it's tilted at a higher angle or whether it's up and down vertically, all I know is that gravity will always be pulling, and I will turn the paper in just a moment, in a straight downward direction to the center of the earth. Okay? No matter what position my object is here, my first arrow is always going to be, I'm 99.99% of the time, I'm going to have some type of weight force or gravitational force. And why? Because I'm here on Earth. I'm going to have a gravitational force. Now, when I draw this vector arrow, I don't know the magnitude. Remember, the word magnitude means number value. I don't know it. But I do know that this is going to be some type of weight force, and as I continue to do my drawings later on, either I would do an FW or I might write it F sub G. And I just go back and forth. I flip-flop between them. Whichever one comes to my brain first, okay? They mean the same thing. Now, my car is being towed or pulled. And here's the actual, it shows me that this truck is going to move in this direction, right? So the stronger force or the applied force is going to be this direction. Okay? Now, it's also, do you see right here? Being pulled upwards because of that tow truck over here. Oops, sorry. So this, what I'm going to do, and I'm sorry that I need to look at my paper this way. This is how I'm sitting. I will turn it back towards you in just a moment. I need to do this for myself personally. I like to do a little dashed line. Okay? This little dashed line is going to help me. This is going to show me that this direction here is going to be my F sub A for my applied force. And it actually should be my longest arrow. So when you start doing these for quiz or test, okay, you actually, again, I'm not going to get a ruler out to measure, but you know that vector arrows, the size of that vector arrow represents the size of the magnitude of it. And the stronger arrow is going to be moving in this direction, the F sub A, because it is moving that way. Now, since it's moving that way, what did I say over here? 90% of the time, the frictional force will be opposite to the applied force. And if I drew my arrow of my applied force in that direction at a little slight angle, then I need to draw, look at this, it must be opposite. I can't draw it this way because that's not opposite to this at an angle. The placement of that object does matter. And we will be practicing this, I promise you. This is going to be F sub F for frictional force. 90% of the time, there's always a frictional force that's opposite to the applied. And I literally mean opposite. That's the reason why I did my little dash arrows. Now, the other thing is we got something here called a normal force. This dotted line here helps me look at the, what's the word? Like kind of like the axis that this is on, okay? And my normal force is always going to be perpendicular and form a right angle to this little dash line that I drew out. So if I was to do that, I can't draw an arrow straight up. I'm going to have to draw it at a little angle. That way it can be perpendicular and form a right angle. So again, I need to look at this way. So here, hopefully you can see it like that. Not only that, my applied force is stronger than my frictional force. If my frictional force was stronger, then my car would come to a slow down stop. But my truck is pulling my car. Now, my weight force is pulling down. My weight force arrow better not be bigger than my applied arrow. That means that my car is sinking into the concrete, and it's not going to do that. Okay? Now, my other one is, again, this is the normal force. Do you see how this is touching in contact with the surface? Then I have to have a normal force pushing up. And it's perpendicular to this dashed line that I drew, which forms a right triangle or a right angle, 90 degrees angle over here. So in this case, my applied force is bigger than my frictional force. My weight force, I just drew an arrow. But this one, which is the normal force, again, if I have a weight force, 90% of the time, the normal force is opposite to it. Okay? It needs to be the same size as my weight force. If I drew this arrow way bigger than this one, then that means that my car is like what? Like the road is bumping it up. And no, the road is solid and still. It's not causing my car to go up. And my weight force is not so strong where it's sinking into the concrete. This is my normal force. And these two forces right here should be equal to each other. This force should be the biggest force. Or the longest arrow. Because it shows me that it's movement in this direction. Okay? Again, we start from the center. Some of the worksheets that we're going to see on homeworks, they don't start from the center. But we know how to do it the correct way. The correct way is to start and draw a dot in the center. Like over here. They have a different example. And we should draw our dot in the center. And they have a normal force pushing up. A gravitational force pushing down. Again, I don't have a ruler. I guess I could get one if I wanted to. But both of those arrows, there's no magnitude with it, but by me looking with my eyes, I can see that the arrow sizes are pretty much the same. Then there's an applied force this way, and there's a frictional force. Honestly, when I look at it, the applied force looks like it's the same as the frictional force, as in like this object, maybe came to a stop or something? I don't know. But I see that it looks like those two arrows cancel out. Those two arrows also looks like they cancel out. This object may be at rest, or this object might be moving in outer space at a constant speed, not speeding up, not slowing down in a straight line, because it looks like those two cancel out and those two cancel out. And we're going to start talking about them, but we will start including magnitude value, which is really going to help us out. Not having a number, we're just kind of estimating or guesstimating what's going on. Okay, I'm stopping here because here's where we're going to start again, some more math. And actually, it's going to be the SOHCAHTOA. So it's going to be a review from last unit. And then we get into our last equation, which is the Newton's gravitational law equation, which is really, it looks like it's scary, but it's not. It's just a really big number that we use. That's the reason why it looks scary. Okay, I'm going to stop here. I'm going to post the videos that we have at this moment. I will come back and I will video later on. Okay, but at this time, what we need for homework number 1, I've already videoed, and so you should be good to go. Alrighty, we'll have more videos up later.